Welcome back to the deep dive. Today we have a stack of papers from Meta Superintelligence Labs that frankly kept me up last night.
It is quite a lot of material to process.
Yeah, it really is. We are looking at SAM3, the segment anything Model 3.
And if you have been following computer vision, even casually, SAM 1 and SAM 2 were big deals.
They were massive. They basically solved the problem of cutting things out of images. But reading through this new report, SAM3 feels different.
It is a significant leap.
Like we are crossing a very specific line from seeing pixels to actually understanding concepts.
That is a good way to put it. If you look at the trajectory, the previous models were built around a task called Promptable Visual Segmentation, or BVS.
Which sounds incredibly technical.
Right, but the workflow was actually quite manual.
Yeah.
You, as the user, had to act as the guide. You provided a point, a bounding box, or a crude mask.
You were essentially pointing at the screen and saying, see this blob of pixels, cut it out.
Yes. The intelligence was in the segmentation itself, not the identification.
Yeah. I had to know where the cat was. The model just handled the scissors.
Spot on. SAM3 shifts that objective entirely. We are moving into Promptable Concept Segmentation, or PCS.
So the burden of identification shifts from you to the model.
Correct. Instead of clicking on a cat, you simply type striped cat.
And the model now has to scan the entire image, or video for that matter.
It has to understand what a striped cat concept looks like, find every single instance of it, and segment them all individually.
Which sounds simple to us humans because we have been doing it since we were toddlers.
But for a machine, that is a massive jump.
It is no longer just grouping similar colored pixels. It has to bridge the gap between the semantic idea of catness and the visual reality of the image.
And that bridge is what this paper really dissects. They achieved this by unifying detection, segmentation, and tracking into one architecture.
Plus, they built a massive data engine to train it. We are talking about scaling laws that just didn't exist for this specific task until now.
The numbers are definitely staggering.
I want to get to that data engine in a bit, but let's start with the user experience. If you were sitting in front of SAM3, what are you actually feeding it? The paper mentions noun phrases.
This is the critical constraint to understand. The model is not a chatbot.
Right.
It is not designed to parse complex, reasoning-heavy sentences.
Yeah.
You cannot type the cat that looks sad because it didn't get fed.
It wants simple declarative noun phrases. Red apple, yellow school bus, running dog.
It is very focused. However, the input isn't limited just to text. You can still use visual prompts.
Right, the image exemplars. I found this part really intuitive. You can draw a box around an object, but you use it as a template.
You are defining the concept visually. So if you draw a box around a specific bolt on a machine, SAM3 interprets that as a command to find all objects that look like this.
But they added a layer of refinement that is pretty fascinating, using positive and negative exemplars.
Because ambiguity is the enemy of segmentation.
The paper calls it intrinsic ambiguity.
Yes. Let's take the word mirror. If I ask you to segment the mirror, do you segment just the reflective glass, or do you include the wooden frame?
It depends on why you need the segmentation. If you are selling the frame, you want the wood.
And if you are replacing the glass, you want the reflection.
But the model cannot know your intent.
Which is why SAM3 allows for iterative refinement. So you type fish, and it highlights the whole fish, but you only wanted the tail.
You don't have to just accept the bad result.
Right. You can draw a negative box over the body. You are effectively telling the model, this part here is not the concept I am looking for.
And the model updates its understanding of your specific fishtail concept in real time. It is like a conversation, but with boxes instead of words.
That is a great analogy.
Let's pop the hood on this thing. The paper describes a unified architecture for both images and video. It seems like they merged a detector and a tracker.
They did, and they share a single backbone, which is highly efficient. They call it the perception encoder.
In SAM2, they used a Hiera encoder, which is great for visual features.
But SAM3 has to understand text, like striped cat. So they needed a backbone with much stronger semantic understanding.
It has to marry vision and language before it even tries to segment anything.
Yes. And on the image side, the detector uses a DETR-based approach, a detection transformer with a fusion encoder.
That fusion encoder conditions the image embeddings by cross-attending to the prompt tokens. But the component that really caught my eye here was the presence token.
It sounds a bit philosophical, but it solves a very practical problem in computer vision.
Typically, when you ask a model to find an object, you are asking it to do two things at once.
Recognize what it is and localize where it is.
But what happens if the object just isn't there? Say I ask for a unicorn in a picture of a kitchen.
A standard localization model might try to force a fit. It might look at a weird shadow on the fridge and say, well, that's the closest thing to a unicorn I can find.
And it gives you a garbage mask. It creates hallucinations because it is biased toward finding something.
Which is where the presence token comes in. It acts as a global gatekeeper.
It is a learned token that looks at the whole image and the prompt, predicting the probability that the concept exists at all.
It decouples the recognition from the localization.
So if the presence token says there is 0 chance a unicorn is in this kitchen, the model suppresses the local queries.
It prevents the system from hunting for ghosts. The final score is just a product of those two probabilities.
Separating the does it exist from where is it seems like the key to making this reliable. Now what happens when we add time? The video tracker.
The video tracker inherits its architecture from SAM2. It treats video as a sequence of frames that need to be connected.
And it operates on a specific cycle. Detect, propagate, update.
First, in the current frame, it detects new objects that match your prompt.
Then it looks at the masks from the previous frame to predict where those objects have moved.
That is the propagation step. Finally, it uses a mathematical function called intersection over union.
Which is just a fancy way of measuring overlap.
It measures how much the new detection overlaps with the predicted track. If they line up, the model confirms it is still the same object and updates the identity.
The paper mentions a memory bank for this tracking process. Is that just storing the previous frame?
It is much smarter than that. If you only look at the previous frame, you risk drift.
Right. If the object slowly turns away or gets covered up, the model might lose track of what it originally looked like.
So the memory bank stores features from past frames. But crucially, it stores conditioning frames.
Meaning the first frame where the object was detected?
It always keeps a reference photo of what the object looked like at the start. It anchors the identity.
That way, even if the cat walks behind a sofa and pops out 3 seconds later, the model can look back.
It checks the memory bank and confirms that the features match the cat we started tracking 10 seconds ago.
Let's move to the part of the paper that honestly stunned me, the data engine. Training these massive models requires data, but the scale here is absurd.
And they didn't just scrape the web. Scraping the internet has diminishing returns.
You get a lot of photos of people, cats, and cars.
But you don't get enough specific, diverse concepts to teach a model to segment literally anything.
To solve this, Meta built a human and model-in-the-loop data engine. It is basically a production line.
Step 1 was media curation. They explicitly hunted for data that breaks standard models: medical imagery, underwater footage, infrared, microscopic images.
They needed diversity. But the magic really happens in step 2, label curation.
They used multimodal large language models to act as AI annotators.
So instead of humans sitting there typing red apple for millions of images, they had an AI look at the image and generate the noun phrases.
Yes, but here's the clever part. They also tasked the AI with generating hard negatives.
Explain that concept. Why is a hard negative so valuable?
If you want to teach a child what a wolf is, showing them a picture of a wolf helps.
Sure.
But showing them a husky and explicitly saying this is not a wolf is much more powerful.
That makes sense. It looks similar, but it isn't the target.
The AI annotators deliberately created these difficult distinctions to force SAM3 to learn the subtle boundaries of a concept.
It learns not just the general shape, but the specific attributes. But this is where I get a bit skeptical. You have an AI generating the training data for another AI.
Right.
If the first AI makes a mistake, like identifying a husky as a wolf, doesn't SAM3 just learn that mistake?
That is a classic risk of synthetic data. But Meta countered this with step 3, label verification.
They fine-tune specific MLLMs to act as AI verifiers.
It is AI checking the homework of the other AI. They check 2 specific things. First, mask verification. Is this segment actually correct?
And second, exhaustivity verification. Did we find all the wolves in the picture, or did we miss one?
The paper claims these verifiers achieved near-human accuracy.
And the throughput must be insane.
By using these AI verifiers instead of humans, they doubled their annotation speed. The result was a high-quality real data set of 4 million unique phrases and 52 million masks.
But that was just the real data. They also generated a fully synthetic data set. And this number jumped out at me, 1.4 billion masks.
38 million phrases, 1.4 billion masks. It is a staggering amount of data.
Usually, synthetic data is seen as filler.
But the researchers found that adding this synthetic data, SACOSYN, significantly boosted performance on real benchmarks.
That is the scaling law they mention. Quantity, when rigorously filtered by AI verifiers, translates directly into capability.
The model got better at seeing real-world objects because it had practiced on a billion synthetic ones.
Oh, so how good is it? They released a new benchmark to prove it works, the SECO benchmark.
Segment anything with concepts. It has about 207,000 unique concepts.
For context, most standard benchmarks have maybe 1,000 categories, so this is 50 times larger.
And on the zero-shot LVIS mask average precision, Salmon 3 scored a 48.8.
Which is huge. The previous best was 38.5. A 10-point jump in these benchmarks is massive.
It effectively doubles the accuracy of existing systems for promptable concept segmentation. And it is fast. On an H200 GPU, it processes an image in about 30 milliseconds.
Video is a bit trickier, though. The paper mentions that latency scales linearly with the number of objects.
That is the trade-off. In an image, the detector runs once. In video, the tracker has to manage every single object you ask for.
If you track 5 people, it is real time.
But if you try to track a crowd of 100 people, the system slows down. It has to update the memory and propagation for 100 separate identities every single frame.
I want to touch on one final piece of the puzzle here, the SAM3 agent. We established that SAM3 takes simple noun phrases.
Red ball, pixel character.
But the world isn't made of simple noun phrases. The example in the paper was the stronger Mario.
This is where integration is key. SAM3 is a segmentation engine, not a reasoning engine.
It doesn't know who Mario is.
And it certainly doesn't understand the abstract concept of strength in a video game context.
So if I type stronger Mario directly into SAM3, it fails.
It would likely fail, or give you a random selection. But the SAM3 agent pairs the model with a multimodal LLM.
You ask the MLLM to find the stronger Mario. The MLLM acts as the brain.
It looks at the image, reasons that stronger in this visual context might mean the larger character, or the one with the fire flower power-up.
The MLLM does the thinking, translates the complex request into a noun phrase SAM3 can handle, like pixel character.
SAM3 finds all the pixel characters and returns the masks. Then the MLLM selects the specific mask that corresponds to its reasoning.
It is a tool use paradigm. The brain uses the eyes and hands to interact with the world.
It allows SAM3 to be excellent at localization without needing to be a master of all human knowledge.
Are there places where this falls apart? The paper seemed pretty honest about its limitations.
Concept granularity is a big one. SAM3 is great at finding an airplane, but zero shot, it likely cannot distinguish a Boeing 737 from an Airbus A320.
That requires specialized domain knowledge that isn't in the general training set.
You wouldn't use it for specific medical diagnoses without fine-tuning either.
And it strictly cannot handle relational queries on its own.
Right. You cannot ask SAM3 for the man holding the cup. It sees man and cup as separate concepts. It doesn't understand the physical relationship of holding.
You would need that external agent we discussed to bridge that logic gap. And on the video side, there was a note about ambiguity in crowds.
The current tracker processes objects somewhat independently. It lacks a shared global context for the video.
So if you have a team of soccer players all wearing the same uniform running across each other,
SAM3 can get confused and swap identities. It doesn't fully grasp the team dynamic to resolve those individual ambiguities.
putting it all together, SAM3 feels like a massive step toward machines that actually interact with the world on our terms.
We aren't just drawing boxes anymore. We're describing concepts.
It bridges the divide between detectors that knew what things were and segmenters that knew where pixels were.
SAM3 fuses them completely.
And it does so on the back of a data engine that is largely automated. That brings up a really provocative thought from the paper to leave you with.
The bottleneck for AI progress is changing.
Right. The paper reveals that AI verifiers allowed for a doubling of annotation throughput.
Which is a fundamental shift in how datasets are built.
If the model is learning from synthetic data, and that data is verified by other AI models to achieve these benchmark scores, it really makes you wonder, are we reaching a point where human annotation is becoming the bottleneck rather than the gold standard?
It is a fascinating question to consider as these systems scale.
Something for you to explore and mull over the next time you look at an AI dataset. That wraps up this deep dive into SAM3. Thanks for listening.
Thanks for having me.